Today, I'm going to talk about the things which most of you already know. And if you haven't read or heard about the subject I'm going to talk about today, this will be in the handout Professor Hosokoshi distributed last week. Okay. Today I'm going to talk about mostly the things which are described here in this handout. Chapter 5, or I guess this is Blundell's book. It's a very good textbook for undergraduate students. Okay, so I start off by more or less repeating what Professor Hosokoshi described or reviewed last week. And most of the subjects I'm going to talk about today and next week are on the so-called mean field approximation. Okay. And the mean field approximation is a method, the simplest method of describing or treating systems made of large number of particles in which the particles are interacting. Okay, you can talk about conduction electrons in which conduction electrons are interacting with each other, or in magnetic cases, the magnetic dipole moment interact with each other. And this is a general term, a general method, and we're going to review how it's used in magnetism, but it shows up in many places in condensed matter physics. It's the lowest order approximation for such a system. Of course, the real lowest order is that you ignore the interaction, but you take the interaction into account. If you did so, mean field approximation is the lowest order approximation. And the two are exactly the same. Okay? But you're going to see how the mean field approximation is done, in particular in magnetism. Okay? Have I been speaking slowly? Do you understand what I've been saying? No? Too fast? Okay, those who think I've been talking too fast, raise your hands. Okay. So I have to slow down. Okay? So I just told you this is the lowest order approximation. In condensed matter physics, okay? In our case, the particles are magnetic dipole moments. Okay? And magnetic dipole moments, because this is rather long term, so people just call them spins. Spins, strictly speaking, are the spin angular momentum. Electrons have spin angular momentum, but we just know, instead of calling magnetic dipole moments, often we use the word spins, all right? And the Hamiltonian of magnetic dipole moments which interact via exchange interaction are written in this way. I have to follow the symbols used. You're familiar. All right? This is the interaction. Now, I use the spin operators, but this doesn't necessarily mean that the magnetic dipole moments come from intrinsic spin angular momentum alone. In general, a magnetic moment of an ion can consist of a spin angular momentum and the orbital angular momentum. And associated with that, you have magnetic dipole moment which is related to this quantity, right, in general. But for simplicity, because J is used here, we're not going to use J. Okay? We're going to write S, but S doesn't necessarily mean that we're talking about only this. Although it turns out to be correct if you deal with 3D ions. You have a magnetic ion which is a 3D rather than 4F, or magnetic dipole moments which arise from radicals. In such cases, L is often 0. Therefore, the total angular momentum is S itself. Okay? So in such a case, this is a good notation. But even if L is non-zero, we don't want to use J here because you have 3 J's. For that reason, people write S. Okay? That doesn't mean that you're dealing with ions in which the magnetic dipole moment arises only from a spin angular momentum. Okay? And we use the word spin, but in a real ion, the magnetic dipole moment may come from J, the total J, but we still call it spin for simplicity. So that's one thing, one reminder. The word spin really doesn't mean it's S. Another thing people do is if you look at it, let's just focus on S because the J is the same. If the spin angular momentum is pointing, let's say up, then the magnetic dipole moment is pointing down, right? But we ignore this difference because it's inconvenient. Okay. Most people treat as if this is the real, this is the reality, but most people just make S and mu in the same direction. Well, you may say, hey, that's wrong. It's not wrong because these two are anti-parallel to each other because people who studied the electricity in the 18th century didn't know, right? Because of that result, electrons ended up having a negative charge. It's very inconvenient. If the people knew that the electrons are mobile, well, this is in the 18th century when the existence of electrons are not known, if they knew, then of course they would have chosen the sign of the charge for the electrons positive. Yeah? Because they decided. They rub ebonite, what did they do? They rub ivory against silk and what else did they do? Amber against wool or something, and then they decide, we call this one positive and we call this one negative. It's just historical accident, right? So if you're going to do electricity and magnetism theory nowadays, then of course you would choose the charge of the electrons to be positive, which is most convenient, right? So this is just completely arbitrary whether they're anti-parallel or parallel. So most people make the two parallel to each other. And the third thing is, of course, S, the operator, correctly is angular momentum. Therefore, it has a unit of h bar. The square bracket means it's the dimension of the unit. But this is inconvenient, so we make it dimensionless. This is what most people do. Therefore, this has a dimension of energy. Okay? So J, the interaction between the ions, you can use either joules, or you can use electron volts, or you can use the Kelvin. Okay? By Kelvin, we mean that you divide it by J divided by the Boltzmann constant, of course, is in Kelvin. But if you're a theorist, you make everything dimensionless. So you say Boltzmann constant is 1, then of course it's Kelvin and Joule, the same thing. Okay? We just choose whatever is, because we are adults, we are not undergraduate students, so use whatever is most convenient. And Joule is very, very inconvenient because Joule is too large. Okay? Electron volts, Kelvin are more convenient. Because you can talk about milli-electron volts. That's a typical interaction. You can talk about 1 degrees, which is a typical interaction. So whereas if you use joules, you have to deal with large exponent, minus 17th or something, okay? 10 raised to minus 17 or something. It's very inconvenient, right? So those are reminders. When you read papers and books, most people use those conventions without telling you, so you have to be careful, right?